Okay guys, let's talk on the topic called LLM inference. So we'll start to discuss about what exactly the people misunderstood from this statement LLM inference. Generally people think inference is just a forward pass. However, in reality, inference is a distributed system problem because it involves the scheduling issues, memory management, networking, queuing and the failure handling. So this is something not confined only to model as one component, and this is not because of the model that it's turned out to be a bottleneck. We'll talk about that in the subsequent discussion. But first we need to understand when does inference stop being a model problem and turns out to be a system problem instead. So as soon as our system moves from the pilot state to production, means wherever we move into a stage where we need to handle multiple users concurrently, the inference turns out to be a system problem. It's the moment we start caring about the tail latency, throughput, and the cost associated. Inference becomes more of a resource orchestration and not only confined to model weights and biases concept. So if we talk about the production inference failure that changed how we simply design the systems. So in concise way, we can say a healthy cluster with perfect dashboard, but 99 P99 latency exploding due to silent KV cache fragmentation. Means even though our system is healthy, but still we are having an issue because of the memory, specifically because of how the fragmentation comes into picture despite using the KV cache. So what do we confine from this is why don't we measure, why you don't measure will absolutely hurt you, what you don't measure instead. So this is something not known beforehand. We remain confined to more about the operational cost for the large language model in production, but it's turned out to be a memory constraint issue and not the compute one. Let's talk on to, if training is the headline, why is inference is the real cost center? Means, or we can say mostly we hear about training the model is hard, and then why it is so that people don't talk about inference if that's the real game changer in terms of cost. In a simple term, we can say training is something that is to be done at one time. It's a one-time complexity that you need to solve, but inference is something that will come forever in picture for every token, every user, and every single day. At scale, inference costs draft training by orders of magnitude instead. So I think enough of on the basics of what inference should be. Let's talk about the core architecture associated with the inference model. So let's see how and where does latency really hide in the inference critical path. Latency basically hides in the queuing process, scheduling decisions, KV cache misses, synchronization barriers and network hops, especially when it's under the load. If we talk about in the today's timeline, where do we see which trade-off matters more today? Is it the throughput, tail latency, or cost predictability? Obviously, I'll say it's a cost predictability. Teams can tolerate slightly higher latency, but unpredictable GPU burn will kill that option as fast as that not even the slow responsive will do. So basically it's a GPU cost, or you can say in simple terms the operational cost. That's the trade-off we cannot bear to live with, and it's a major problem to solve here in today's time. Let's talk about how do we think about prefill and decode optimization. These are the two aspects that comes into picture when we talk about the inference pipeline. So how do we answer this? Is like prefill is bandwidth bound and it's bursty. It's bursty because it is more memory confined, or memory put memory under the stress, and decode is more latency sensitive and iterative. Both of that, both either prefill or decode we talk about, they need different batching and scheduling, and also the memory strategies. We can't treat them both as same, because in a single line we can say prefill is something more memory memory critical, and decode is critical from the perspective of compute and the operational cost. So let's see, why does batching took easy on paper but eventually fails in the production? Because we understand the real traffic is spiky, heterogeneous, and impatient. Batch assume uniformity, and user don't behave that way. It's simple in that terms. So what does first breaks when there is spike in the traffic? Usually the schedulers, then goes the KV cache, and eventually the GPU memory. Once scheduling fairness breaks, everything that comes in the downstream degrades very fast. Let's hop on to the another component that's very critical from the perspective of inference pipeline, called KV cache, memory, or maybe attention algorithm we talk about in the model world. So let's see why KV cache is the silent killer here. Because it scales with the sequence length and doubles when concurrency comes into picture, and that too invisibly, and fragments over the time until performance collapse without obvious alarms. What does page attention solve and what not? Page attention solves memory fragmentation and resource allocation, because it makes it possible to have a non-contiguous resource allocation, more dynamic. However, it doesn't solve the poor scheduling or the bad batching and on the external factors like bad traffic patterns. Let's see how bad the fragmentation of the KV cache can turn out to be in case of long running clusters. How bad it could be. It could go as bad as that restarts becomes the only way for performance optimization. If you need periodic restarts, you don't have a memory under control, it means, and that's some real challenge here. Will KV cache move off the GPU? The next question comes in picture. We can say maybe partially yes, by using segregation of the memory, be it into multi-tier like GPU, CPU, and then in-memory cache. But GPU resident cache will remain critical for low latency path, because the eventual calculation turns out to be at GPU, where the matrix gets multiplied, and this is what has surely going to have a very critical impact on the how we deal with the KV cache. So if we see what turns out to be the hardest part of serving long context models as of today, obviously it's predictability, because long prompts turn memory and latency into moving targets, and we don't have any control on that, and that turns out to be the hardest part when we intend to deal with the long context models. Let's talk about the performance and optimization. What's the biggest win we have achieved in the in the past lately? Is it quantization, batching, or scheduling? It's scheduling. Why we say that? Because we can't quantize our way of bad scheduling. Bad scheduling has to happen properly, then only, otherwise the downstream, whether you do quantization, you do the batching, that's not going to help. Let's talk a bit on the GPU side and understand where do CUDA graphs help and hurt. They help with the stability, repetitive workloads, but they hurt when the workloads are dynamic. Graph breaks, destroy gains. Speculative coding. Is it an overhyped or underused? It's obviously a powerful but Operational complex. Most teams stop on paper because it's good in the case where latency is not the primary concern, but the pattern or your prompt are quite repetitive one, and that's generally not the real case scenario we see in the real time whenever we are deploying a model to the production. Let's talk about the most misleading inference benchmark. It's single prompt latency benchmarks, because whenever we are giving a simple prompt for evaluation, we are ignoring the concurrency, the tail latency, and even the cost that comes in the picture, where actually comes the reality. Tile precision. If we talk about balancing accuracy loss versus cost with int8 or FP8 precision, then we say that tie precision to user visible quality, not model metrics. If users can't tell, you are overpaying. Means, if users are not able to see any difference in the precision, we need not to invest explicitly on attaining the precision at the GPU level. Because if we move from FP8 to int8 or for single bit quantization, we might save a lot of cost, because we are able to fit the high-end models on the less memory, which in other terms helps us with the cost effectiveness and improve the cost of do the cost optimization and brings down the operational cost. So systems, infra, and inference ops. So if we see what's the major difference between, if we talk about inference ops or ML ops. ML ops is something that's confined to models getting trained, but inference ops keeps models fast, cheap, reliable, and alive under the real traffic though. Debugging latency spikes when dashboard looks fine. Correlate queue depth, scheduler state, KV cache usage, and request mix. Latency lies when you only look at averages. So what are the metrics that actually matter in case of inference? Is P95 by P99 ratio latency, tokens per second per dollar, KV cache utilization and evacuation strategy, and the queue wait time that defines how fast the tokens are getting generated. So what's the safe bet? Is it blue, green, or the canary for LLM serving? We should basically route by request class and not percentage. So prompts behave differently, so we need to treat them as a workload. What's the most common anti-pattern? It's like we are treating LLMs like stateless REST APIs, but they are basically stateful, memory-hungry system. Means, though they are stateless, but they deserve a memory. So we need to bring in and solve the problem of why LLM forgets, or we need to come up with the solution where we can make the LLM models remember the history and define the context properly. Let's see if we talk from the perspective of business reality in terms of the cost and financial operations. Where do we see the companies overspend unknowingly? It's primarily on GPU being idle, over precision unnecessary, that's not required or being observed by the user, and the unused context windows. So what we need to see, is it cost per token or cost per user? That is more relevant for us to understand from inference. We need to optimize per user, because eventually it's the user or the customer who is going to drive the business, but not the tokens. What's the hardest part of forecasting inference cost? It's like user behavior. We never know. One power user with long prompt can blow your model overnight. Build or buy the inference infra. Obviously, we need to build our own inference. It's going to be a core IPs, but when it's plumbing, but understand what we are actually outsourcing. So if we are confined to more core IPs, we should go for our own inference system. So where do we see inference in 2-3 years? That sounds unrealistic today. Maybe inference aware models co-designed with hardware and schedulers. Will architecture changes reduce pain? They'll shift it. Like model of expert, that's MOE, reduce the compute but increase the system complexity. So if starting today, what we should design differently actually. So from LLM pipeline perspective, we should do inference first, in which we need to figure out our API should be schedule aware, then memory as a first class source, then we should look into the cost observability from the very first day of the inception of inference pipeline. So if you talk about what exactly is one mistake that every new inference team generally makes, I understand it's more like we are ignoring the tail latency, which until customer comes up with a complaint. Let's conclude the talk with one last signature question, and wherein we are going to say what exactly we can term as one lesson that we learned after breaking the production. Yeah, obviously we can say inference doesn't fail loudly, but it degrades quietly, expensively, and at scale. Indeed. Thanks for being there on the discussion. I think we had a wonderful discussion today. Let's see how Eddie gonna do this.